The handiest way to gain insight from the data is to visualize it. However, doing so isn't always straightforward. A case in point is when the range of the data is unbounded. Since the visualization medium, like the screen, is finite, fitting infinitely large values onto it requires a trick. As an example, consider plotting asymptotic functions. When we plot such functions, we draw horizontal asymptotes to show that the output of the function tends to a certain value as the input tends to infinity, and we draw vertical asymptotes for the opposite case. So there exists a hack for visualizing infinities on the horizontal and vertical axes, but what about the color axis? To be clear, the question I'm raising is how can we assign colors to values when the range of values is not bounded? I will elaborate on this using a concrete example. Imagine we have a map of a country and its division into provinces. We want to assign a color to each province based on its ratio of water supply to water demand. I will call this ratio R, and throughout this video, whenever I say R, I'm referring to this ratio. Let's zoom into an arbitrary province. Basically, water supply is the amount of water that naturally flows into a province, for example through rain and rivers. And water demand is the amount of water that's used for agriculture, industry, domestic purposes, etc. For better demonstration, let's show the supply and the demand with a green and a yellow rectangle respectively. Now back to our map. Our colors will be picked from the color map on the right, which is a linear gradient from yellow to white and from there to green. In a balanced situation, the supply of a province is equal to its demand, and the ratio will be equal to 1. In this case, the color that should be assigned to the province is white, right from the middle of the color map. If the supply is slightly smaller than the demand, the ratio will be slightly smaller than 1, and we pick a light yellow color. On the other hand, when the supply is slightly greater than the demand, we pick a light green. This logic remains the same when R values deviate further from 1, except that we pick brighter colors. In an extreme case where there's no supply, the ratio will be equal to 0 and we go all the way down the color map to pick the brightest yellow. Conversely, as the demand tends to 0, the ratio tends to infinity and we pick the brightest green from the top of the color map. So we know exactly what color should be assigned to a province when its R value is 0, 1 or infinity, but what about other values in between? I will answer this question in this video so that in the end we'll get a colorful map. Before diving deep into the math, I want to point out that the same problem appears in domain coloring, a technique in complex analysis where complex functions are visualized using color on the complex plane. Here we will stick to our somewhat practical problem, but the main idea can be used in domain coloring. And with that, let's break into the solution. We will start by assigning numbers to our color map. Here the brightest yellow is set to 0 and the brightest green is set to 2. We could choose any arbitrary pair of numbers instead of 0 and 2. For now, these numbers have nothing to do with R values. For all other colors in between, its corresponding number is linearly interpolated. Since white is located in the middle, its corresponding value is 1. Let's assume that our color map is continuous, which means for every number between 0 and 2, there's a unique color corresponding to it. In fact, on a screen, only a finite number of colors can be shown, but let's ignore that. Throughout this video, I will refer to these numbers as C values. Now all we need to do is to find the function f that maps R values to C values. Therefore, we can find the corresponding color for each R. We know that R values can be any number greater than 0, and C values can be any number between 0 and 2, so the domain and the range of f are known. Let's list all the conditions that f should satisfy. As we saw before, when R equals 0, we should pick the brightest yellow, which means C should be equal to 0. And we can write that as f of 0 equals 0. When R equals 1, which means supply and demand are equal, C is also equal to 1, which means the color should be white. So we can write f of 1 equals 1. And when R tends to infinity, C tends to 2, which can be expressed as a limit. The function f needs to be continuous so that there's no jump in colors, and it should also be strictly increasing so that any increase in R results in some increase in C. But two of these conditions are not compatible. It's not possible to have a strictly increasing function with this domain and range. I won't go through it, but luckily, all we need to do to fix this is to exclude 2 from the range of the function. Now all these conditions are compatible. There's one more condition that needs to be satisfied. The problem we are analyzing has some sort of hidden symmetry in it. Imagine you have two provinces, one whose supply is A and its demand is B, and therefore its R value is A over B. And another whose supply is B and its demand is A, so its R value is B over A. If we set R1 to X, R2 will be 1 over X. The situation for these two provinces is exactly the opposite. This should be reflected in the colors we assign to these provinces. If C1 is a light green, C2 should be a light yellow. If C1 is a bright green, C2 should be a bright yellow. But how can we formulate that? Let's assume the difference between C1 and the middle of the color map is delta. Then C2 should have the same difference in the opposite direction. So we can write these two equations. To get rid of delta, we can simply add both sides of these equations. Then we can replace C1 and C2 with f of R1 and f of R2. Finally, by replacing R1 and R2 with x and 1 over x, we get this nice equation. With this equation, you might find some of the previous conditions redundant, but let's keep all of them. There's another way we can interpret this equation. We're using this color map, and we're computing this ratio. If we turn the colors upside down and invert the fraction, we are guaranteed to get the same colors for all supply and demand values if this equation holds true. At this point, I encourage you to pause the video and see if you can find a function that satisfies all these conditions. If you're not going to do so, at least make a guess. How many solutions do you think exist for this problem? Maybe there's no solution at all, or maybe there's only one unique solution, or a finite number of solutions, or infinitely many solutions. Okay, first, let's try to figure out the general shape of the solution. We know f of 0 is 0, so the function passes through the origin. It also passes through 1 and 1, and y equals 2 is the horizontal asymptote of f. So we should expect f to look like these curves. Now let's see if we can find any solution. I'll start with a guess. A linear rational function would be a good initial guess, because if f of x is a linear rational function, f of 1 over x will also be linear rational. So chances are when we add these two, numerators and denominators vanish, and our equation will hold true. This function has 4 parameters, but we know c cannot be 0 because if it's 0, f will be a linear function, not linear rational. So we divide everything by c and rename variables to get 3 independent variables. Then we can use these 3 equations to find the unknown coefficients. If we do so, we get f of x equals 2x over x plus 1. f of 1 over x will be 2 over x plus 1. So if we add these two, we can see that this function satisfies the equation. We can plot the function and verify that it satisfies all the conditions. We can also replace x with x to the power of p for any real positive p, and the function will still satisfy all conditions. This is what we get if we set p to 3. And this is what we get if we set p to 0.5. Once we figure out that the mentioned family of functions satisfy all our conditions, it's not hard to come up with general rational functions as solutions. Here's one example, but infinitely many of these can be found. There's also an elegant solution for this problem from trigonometry. Assume we have a right triangle with side lengths of 1 and x. The sum of two acute angles of this triangle equals pi over 2 radians, so we can write alpha plus beta equals pi over 2, and then replace alpha and beta with arctangent of x and arctangent of 1 over x. In fact, this is an identity for any positive x. Starting from here, with a little manipulation, we can find a function that satisfies our equation. we can draw this function and make sure all conditions are satisfied. The logarithmic function seems to be a legit candidate since we know logarithmic scales are very helpful in data visualization. Starting from this identity, we can play around a little bit and find a function that satisfies our equation. However, if we plot this function, it's clear that not all conditions are satisfied. The log function can be ideal for when we are working with very small numbers or very big numbers, but it cannot handle zeros or infinities. Now it's a good time to see how we can use these functions for coloring. Let's pick one of these functions that satisfy all conditions. Given this function, what color should be assigned to an arbitrary value, let's say 6? To find the corresponding color, we can scale our color map so that it fits the 0 and 2 interval on the vertical axis. We draw a vertical line from x equals 6 to reach the function's graph, and a horizontal line from there to cut the vertical axis. Where we end up is the corresponding color to our value. You see this process is being repeated for other whole numbers. The same can be done with a smaller step size, or it can even be done continuously. For comparison, here's another function and its corresponding color distribution. Here's a function that satisfies all conditions except that it's not strictly increasing. Can you imagine how the colors will be assigned to values using this function? Here's the answer. Since our problem has infinitely many solutions, it makes sense to ask what is the best solution. Picking one solution as the best one requires a precise definition of what we mean by being the best. Rather than taking a rigorous approach, I want to address this question only based on intuition. Here are two functions and their corresponding color distributions. Let's admit that it's very hard to build intuition about something that is unbounded. And because of that, we focus on the yellow part. This curve starts with 0 slope, and therefore at the beginning the change in color is not detectable. In fact, the slope of the function at each point determines how well we can identify changes in the input value by monitoring changes in the color. The other curve starts with a very high slope, so a small change in the input value at the beginning results in a very rapid change in color. As the input increases, the slope of the function decreases and the change in color becomes more dim. So loosely speaking, what I want to conclude is that the slope of the function is like a limited resource and it should be spent wisely. And by wisely, I mean uniformly, because all parts of the 0 and 1 interval are equally important for us. A function with uniform slope is a linear function. We know it should pass through the origin and 1 and 1, so what we get for the yellow half of the color map is the line y equals x. But how should we continue this function? Let's write our function in a piecewise format, dividing it into two subfunctions. For values between 0 and 1, f of x is equal to x, and for values greater than 1, it's defined by some other function g of x that we don't know yet. We know f should satisfy this equation. Let's assume we want to make this equation work for values greater than 1. Since x is greater than 1, we replace f of x with the second subfunction g of x. And again, since x is greater than 1, 1 over x is between 0 and 1. So for f of 1 over x, we should use the first subfunction and write 1 over x itself. This should be equal to 2, and we get to find g of x. We can draw the function and see all conditions are satisfied. Here's the corresponding color distribution. If you pay attention, you'll see that not only is this function continuous, it's also differentiable at x equals 1, where the two subfunctions meet. We didn't explicitly force it to be differentiable at x equals 1, so do you think it's by chance, or there's a reason for it? What we just did motivates a new way for finding piecewise solutions. Instead of drawing the line y equals x, we could draw some curve, let's call it h of x, and then continue it with the same idea we saw. It's easy to verify that if h of x satisfies these conditions on the right, then f of x, defined like this, will satisfy all the conditions on the left. The conditions on the right basically say that h of x should be a continuous and a strictly increasing function that connects the origin to 1 and 1. Let's see some examples. We can draw 1/4 of a circle and continue it like this. We can do the same with a wiggly function like this. Again, you can see the functions we came up with do not have a sharp corner at x equals 1. You might want to figure out why this is the case. Okay, let's go back to our map. These are the R values for each province. This is what we get if we use the best function we found for coloring our map. By using different functions, we get different colors. Here you can clearly see how well each function can distinguish between values. There's only one thing left to do. We don't want to show values on the map itself. We want to show them on a color bar. Instead of C values, we want to have R values here. We know that the bottom, the middle, and the top of the color bar correspond to 0, 1, and infinity. But we need to show more values. The functions we found map R values to C values. Here, we want the opposite. C values should be mapped to R values. So we have to find the inverse function. For this function, its inverse is also a piecewise function. We can simply input C values from 0 and 2 interval to the inverse function and get corresponding R values. And that's it. Now we have everything that is required to show infinitely large values with color. In the end, I want to thank all my friends who kept me motivated for creating this video and helped me improve it with their valuable feedback. Without their support, I'm not sure if I could finish this project. Hope you've enjoyed this video and thanks for watching.